Hello, my name is Ari. I'm a fellow software engineer at Activision, and today I'm going to talk about large-scale global illumination in Call of Duty. So this talk is about global illumination in the context of real-time games, and I wanted to start by highlighting some of the scalability challenges we faced during the development of our recent titles. First of all, in order to render large maps at 60 frames per second across multiple hardware generations, our engine relies on precomputed lighting techniques. However, at the same time, we want to keep our download sizes small for better user experience. And this creates a conflict with increasing scene sizes. I think a good example of this trend is the blackout mode that was introduced with Call of Duty Black Ops and Warzone that was released after Modern Warfare 2. So basically, you have these computationally demanding maps where 100 or more players are competing against each other at any given time. We've talked about various parts of our lighting pipeline before. For example, last year at SIGGRAPH, we presented the Umbra system and how we combine precomputation with dynamic lighting and how we use ray guiding for variance reduction. And you can find papers and talk slides at research.activision.com website. Today, I'm going to be talking about the large-scale global illumination system that, among other things, is used in Warzone, which is the big map game mode. And this talk is going to be like a journey through the large-scale precomputed lighting pipeline. I'm going to start by briefly going over how we sample and represent illumination. And then I'll present the general DERINGING scheme for spherical harmonics and conclude the talk with a new method for high-quality compression of precomputed lighting data. So let's start with how we represent the illumination in the game. To give you some context, here's a screenshot of one of the single-player campaign maps from the latest Call of Duty Black Ops Cold War game. And this scene is fully lit by the large-scale global illumination system, which uses a unified lighting representation based on irradiance volumes. And the nice thing about irradiance volumes is that they provide a seamless unified lighting solution, and they integrate very nicely with both static and dynamic geometry, as well as volumetrics and particles. And if we take a look at a simplified view of this scene, we can kind of visualize the voxels of the irradiance volume. The idea is that each voxel here stores the irradiance in some directional basis, like spherical harmonics, for example, and that allows us to reconstruct directional irradiance at any point in the scene. But using a dense volume is not scalable, since the memory usage quickly limits the volume resolution that we can use. So the usual solution in this case is to use some sort of adaptivity, where the adaptation mechanism can be based on either a single or multi-level spatial hierarchy, or maybe a hash lookup. In any case, I think some care must be taken to ensure that the reconstruction is continuous at block or hierarchy boundaries. And while this is not difficult to do, it can add some computational or a memory overhead, depending on how you implement this during the reconstruction. We decided to take a slightly different route to handle adaptivity, and our approach is based on warping the irradiance volume domain to encompass the sparse detail areas around interesting bits of the scene, like the forest and the trees here. So to reason about these sparse detail areas, we shoot feeler rays from above and below the scene to obtain depth bounds for the map. And based on the rays that we shot from above and below, we obtain this detail shaded region that's shown in yellow over here. Now, if we want to do a lookup, we simply need to compute the normalized height at each point and do a regular 3D volume texture lookup using this normalized height value or warped height value. And effectively, what we've done here is we have warped the irradiance volume around the sparse detail areas. So we have adaptive height resolution everywhere in the scene. And if we smooth out the height changes to minimize the warping artifacts, so the height changes smoothly, there's no abrupt changes, we can guarantee that there are no seams or visible warping artifacts. And what this gives us is an adaptive warped irradiance volume, where the reconstruction is always continuous, so we don't need to worry about block boundary artifacts or patching together hierarchy levels or anything like that. Okay, now that we know how we represent the lighting, let's take a look at how we sample the lighting. So here on the left, you can kind of see the reference irradiance on a very cloudy day in one of our ground war maps from Modern Warfare 2, without any materials, of course. And then if you look at the right, this is if you perform just naive volumetric sampling. So for each voxel, you pick a random position, and then you pick a random direction, and then kind of shoot the final gather ray. This is what you would get. So the problem here is obvious. You get these leaking, light leaking artifacts or darkness leaking artifacts everywhere around the scene. And this kind of light leaking that we saw here is unfortunately a fundamental issue with volumetric light representation. And it's basically due to a mismatch between the voxel resolution and the geometric feature size. And one common solution to this thing is to split the indoors and outdoors into different volumes to prevent this kind of light leaking. And this has been used in multiple games before. However, this still requires artists to manually mark up these areas. And if you have non-boxy shapes, like for instance, here you have a roof that has this kind of V-shaped ridges, it requires a lot of planes and potentially a lot of work for the artists. Another common thing that you can try to do is to modify the reconstruction filter to take the normal into account. That helps in many cases, but it's not foolproof either, as it doesn't really fix the root cause, which is a mismatch between the resolutions of the geometry and the volumetric representation. So we can try to reason about this light leaking problem in this simple case. So what we have here is a building with a door of some sort, and then we have large voxels. And we have the voxel centers here visualized. And these voxels overlap the building as well as they overlap the ground. Now we can focus on this particular voxel over here. And when we're doing this naive volumetric sampling, what we do is we pick a position in the volume, and then we pick a direction and we shoot a ray. And in this case, we hit the sky dome. And then we splat this contribution to the trilinear neighborhood of these voxel centers. Now, if we continue this process, we shoot another ray. In this case, we hit the roof of the building. We kind of a gray sample over here. And as we continue this process, we are computing the average of the samples to get our Monte Carlo estimate of the irradiance affecting this voxel. And then we just continue this process until we've exhausted our sample budget. And in the end, we end up something that's a mix between light values and dark values. And pretty much what we end up with is something like this. That looks, somewhat right, but in areas it's just completely wrong. It's not desirable to have these artifacts at all. The reason for this light leak is that we treat every positional sample within this voxel footprint as being equally important. However, in this case, we have some extra knowledge. We know that the player is going to be, in general, further away from this voxel, and in general, the camera will be in outdoor region. At least if we think in terms of probabilities. What's the probability that the player location or the camera location is outdoor versus indoor? And then that gives us a prior distribution for the camera positions that we can utilize. And the idea is that we want to incorporate this prior probabilistic model of the camera locations into the model. And we call this visibility-based sample validation. And the idea is as follows. So first, we generate a set of potential sample points. These are just 3D positions in the voxel. And then before we compute the voxel value itself, we shoot these visibility validation rays. In this case, this indoor sample, we shoot a bunch of rays. We know that all the ray hit locations are quite nearby, so we consider this sample as invalid and we reject it. We go on, we continue, and in this case, we have a sample that's located above the roof. We shoot a bunch of validation visibility rays. And the hit distance is really far, and we see the sky, so this sample is going to be valid. And then we just continue this process for every sample. We shoot the validation rays, and based on the hit distance, we either keep the sample or discard the sample. And at this point, in this case, we have split the sample set or the potential sample set into two. So we have all the green samples that have a large visible region, and then we have the red samples that have a really small visible region. And the validation criteria we used is just based on the hit distance. If the validation rays see farther away than, say, some fixed threshold, we mark the samples as valid. And the last step, we just killed the invalidated samples, and at this point, we use these green samples as usual. So from each green sample, we shoot a bunch of directional rays, and then based on the trilinear weighting, we splat the contribution of these directional rays to the trilinear footprint of all the voxel centers that they affect. And now we can look at the results when we are using this visibility-based sample validation. So on the left here, you can see the visibility-based sample validation. And on the right, you can see the naive volumetric sampling. And as you can see, the visibility-based sample validation fixes pretty much all of the light or darkness leak issues that we saw on the roofs. However, we still have nice lighting detail under rooftops, under doorways and windows. Wherever you have visibility into indoor areas, you expect to see a shadow, and that is indeed what you get. And here is another example. So you can see the darkness leaking from inside when using just the volumetric sampling. So you get these ugly splotches of darkness around the building. And if you use the visibility-based sample validation, you get rid of all these darkness splotches. And you still maintain a good amount of the shadow detail in shadowed areas and doorways like here. And here is another viewpoint. So as you can see, you have doorways that are open. You can have some tight areas like this, which still maintain shadowing detail, but you kind of get rid of all these dark splotches that are caused by the mismatch between the geometry and the light representations. The remaining splotches are pretty much just Monte Carlo noise at this point. Okay, so at this point, we know how to sample lighting data and how to represent it using our adaptive warp irradiance volume structure. And next, I wanted to discuss a problem that's related to spherical harmonics and low-order representation of physically based lighting signals. Now, the basic problem with spherical harmonics is that if you perform unconstrained least squares projections to SH basis, you can easily get ringing artifacts and color shifts. And the end result might not be a physically based or physically plausible input signal. For instance, in this case, we have a reference irradiance encoded in second order SH. And then if we simply do the least squares projection to first order SH, and in an orthogonal basis, you can just drop the second order basis functions, this is what you get. And what you see here is area where this actually goes to non-negative values, as well as you see this color shift to red that's not supposed to be there. So there are two common solutions to fix these artifacts. First, we can window the higher order coefficients by shrinking them towards zero in order to make the reconstruction non-negative. And for instance, Peter Pike Sloan used this searching routine to find the minimal windowing coefficient. And this problem also has a simple analytic solution for linear SH. And then on the other hand, we can also modify the reconstruction. So Hazel modified the reconstruction to interpolate between the directional and non-directional components to satisfy non-negativity. And this approach is kind of limited to linear SH, since if you want to generalize this to higher orders, it's not straightforward how to do so. And another problem with non-negativity constraints is that it might not be enough to prevent color distortion. So this is the projected irradiance we had from before, and this is the result after we apply windowing. So this means that this is non-negative function over the sphere, but you can still see the red color shifts in parts of the sphere. That's a non-desirable property of this projection. And so in this case, I think it would be more useful to apply more general constraints. What if we say want to constrain the projection to stay within certain color space bounds? Kind of an idea that's borrowed from temporal AA deghosting methods. And the problem with this is that when you think about general pointwise constraints, like these color space constraints, using the spherical harmonics representation, you quickly come to the conclusion that it's not really easy to reason about those. And this is because, similar to Fourier series, SH expansion gives us like a frequency domain representation of the target signal. So for instance, here the target signal is fx, and then we represent it as a linear combination of spherical harmonic basis functions, which have a global support over their domain, which is the sphere. And to obtain the coefficients in this expansion, what we need to do is we take the inner products of the target function and the basis functions. And this is because the spherical harmonic basis is orthonormal. Now, let's imagine what if we had a different sort of representation where, okay, we have some basis functions k tilde over here, but instead of coefficients, we would have the target function values at a set of points xi, and the xi are just points or directions on the sphere. And I like to call this the spatial domain representation, and as opposed to the frequency domain representation that you get when you expand your target function as a linear combination of spherical harmonic basis functions. Now, a natural question to ask at this point is that we have this relationship between the coefficients, the basis functions, and the inner product in the case of frequency domain representation. Now the question is there a similar sort of relationship between the coefficients, which in this case are just the target function values at a certain fixed set of points xi, and inner product with respect to the basis functions ki, and the k tilde, you can think of those as the dual basis functions, and I'll clarify what that means in a second. And it turns out that this answer is yes, and the connection here is given by something that's called reproducing kernels. And so here again, for reference, is the spatial domain representation that we would like to have, so we can impose constraints on the function values themselves more easily. And the way we do this is to introduce this function that's called reproducing kernel for the point xi. And if you define this as a product or sum of product of these spherical harmonic basis functions, and you write the inner product out, it turns out that if you define the kernel function this way, it has this property that's called the reproducing property, which means that if you take the inner product between your target function f and the reproducing kernel for the point xi, ki, it gives you the target function value at the point xi. Now, because of this reproducing property, we can actually write out this basis expansion, the spatial domain representation, using simply the inner products here, which correspond to the function values here. What you can see here is that the ki's here represent our basis vectors, and the k tilde here, they are the dual basis vectors. Now I wanted to demystify this ki a little bit. So if we write this out in a different form, kind of instead of xy, we generalize and just say it's a function of x and y. And I define this the same way or analogous way to this expression. This is what we call a reproducing kernel for the order L spherical harmonics. And if you recall the addition formula for spherical harmonics, you note, or you can immediately see basically that the reproducing kernel for order L spherical harmonics is simply a sum of zonal harmonic functions. Okay, so in other words, the basis vectors we have here are just the sum of zonal harmonics evaluated at the particular direction given by the fixed point or direction xy. And of course, if we want to obtain a basis, we need to have enough of those basis vectors, and they need to be linearly independent. But this is really easy to satisfy as long as the directions xy here are distinct. So you select distinct points on the sphere, then you obtain linearly independent set of vectors, you obtain a basis. The next question is, what is the dual basis? And once we have this complete set of basis vectors, typically what we do is we can use the bi-orthogonality conditions to completely and uniquely define the dual basis vectors k tilde over here. Now, if we have more basis vectors than we need, what we have is not a basis, what we have a frame. And if we have an overcomplete frame over here, and the K is just the kernel matrix where we take the kernel vectors evaluated at each point, x, y, put them into the columns of K, and that's our kernel matrix K. Because it's overcomplete, we know that K times K star, or K, the adjoint of K transpose, is invertible, and we have what we call a canonical dual, which is basically a reasonable choice for the dual basis in case of an overcomplete frame. Together, the dual basis matrix and the basis matrix and its adjoint or transpose in this case, they define two change of basis operators that we can apply to go from frequency domain representation to spatial domain representation and vice versa. So if we start from, so here, y is the target function evaluated at this fixed set of points x, y. So we just take these function values, stack them into one long vector, and we get the spatial domain representation in terms of the dual basis functions. And the coefficients are given simply by the target function values at the points x, y. If we have this spatial domain representation, we can use the dual basis matrix to go to a frequency domain representation, and the C is simply a vector of SH coefficients, right? And then we can do the same thing once we have a frequency domain representation C, which is just a vector of SH coefficients. We can use the adjoint of the kernel matrix to obtain our spatial domain representation. Okay, so these two operators, change of basis operations, are really important in the next step. Now, this is where they come into play. So our main goal here is to apply DERINGING by introducing these color space constraints. So what we do is we take our irradiance function, the reference irradiance function, we compute the min and max color values, and it turns out that it's actually useful to do this in YCOCG space, since it decorrelates the chordal channels pretty well. And we want an SH projection that sits in this color space bounding box. And this color space bounding box lives actually in Rn, where n is the number of sampling points we have over here. Now, and this is the benefit what you get by doing this constraint projection. So I'm going to explain the method in a second. I just wanted to give you a taste of the results that you can obtain with this reproducing kernel Hilbert space framework that we've been kind of setting up so far. So this was the windowed irradiance function, and it introduces a non-negativity constraint, but it still had the issue with red color shifts over here. Now, if we apply or introduce this color space bounding box constraint, the result is shown over here. And you can see there's no red color shift anymore. And you can see that it quite closely matches the reference second order SH over here. And you can see that the problem area that's inside the green circle here is very different from what you get when you introduce just a non-negativity constraint. To apply this constraint, we use the method of alternating projections. And the idea here is that the feasible region in the spatial domain is a convex set. It's an intersection of all these half spaces, and the convex set resides in Rn, and n is the number of points x, y we use for the spatial, overcomplete spatial representation via reproducing kernels. So what's the method of alternating projections? So the basic idea is that we project to the two different convex sets iteratively. And we start with the SH representation of the target signal. This is called the CK. And then we go to the spatial domain using the adjoint of the kernel matrix. And here is the key step. We apply a projection operator that encompasses our constraint. and this happens in the spatial domain or point-wise domain. And in the case of bounding box constraint, the key idea here is that the projection operator in the spatial domain is very simple to evaluate. It's simply the clamp function. So it clamps the values to the bounding box, and that's it. And then once we have done the projection in the spatial domain, we use the dual kernel matrix to go back to the spherical harmonic domain to obtain our next iterate. Now, since we are doing these alternating projections on the convex sets, we know that this operation or this iteration will converge to a point in the intersection. And we already know that the intersection is non-empty, since the mean color or the DC color is clearly between, it satisfies all these color space constraints. Now, this idea can be extended to other constraints very easily. So all you need to do is modify the projection operator. So for instance, if you want to apply a non-negativity constraint, that's simply another clamp or another max operation in the spatial domain. Very simple to do in the point-wise domain. And the key takeaway here is that this reproducing kernel based change of basis allows us to write some convex constraints in a very simply and practical way in the spatial domain. And we have this simple algorithm that allows actually to compute the resulting projection by iterating on these simple convex projections. And I think this framework for thinking about constraints have a lot more applications than this. For example, we can apply domain constraints like introduce hemispherical or spherical cap restrictions. And we can do this without the need of solving the eigenfunctions of the Laplacian over this maybe even complicated domain. Now, you can, if you do this, or if you use this reproducing kernel Hilbert space approach, the main benefit is that all your end vectors are still just SH vectors. So you can combine the same SH vectors with other operations without the need to do any change of basis from a specialized hemisphere basis or a specialized hemispherical cap basis and so forth. And for example, here's our reference irradiance function. And this is the least squares projection to first order SH. And here is just a simple example of doing a hemispherical constraint where the projection is constrained to match the target function or the reference function on this visible hemisphere. What happens on the backside, we're never going to see it. It looks way worse. But the key idea is that in this area where we introduce the constraint, it more closely matches the reference than a simple linear SH projection. And what you have here, the resulting C, that's the spherical harmonics coefficient vector, is just a spherical harmonic coefficient vector. You don't need to do any change of basis from this constrained hemispherical basis to the SH basis because you're already working in the SH basis. So I think that's pretty cool. Okay, so at this point, we know how to sample, represent, and fix some ringing issues with our input lighting data. And the last part of this talk covers how we fit all this data into memory. And to give you some motivation, I wanted to revisit the scene I showed you before. And this is one of the single-player campaign maps from Black Ops Cold War. And if we disable all the material textures, we can see the lighting a little bit better. And finally, if we disable the direct sunlight, we are left with the pre-computing lighting data only. And you can see that it plays a big role in this scene. And all the volumetrics, particles, and geometry is lit by the pre-computed lighting data. Now, if we think about the memory usage for this map, and if we place just a simple linear SH RGB irradiance volume that's reasonable in resolution over the scene, and then compute the source data, we already are at 1.5 gigabytes. So that's a big problem. We can't achieve anything like that. And in the rest of the talk, I'm going to go over our new technique to compress this lighting data to satisfy the memory constraints and how you can obtain a fast and seamless reconstruction from the format. So I wanted to start with some related work and linear dimensionality reduction in particular. where the setting is that we have some high dimensional target data where D can be from 10 to say 3 to 400. And then what we want is a simple representation in terms of some basis functions. So we seek a linear combination of basis functions where the basis functions BL, they live in the same high dimensional space. And the basis coefficients CL, they are just scalars. And for this to be a good approximation, we need the reconstruction error to be small in some norm. Also, the number of components in this linear combination, it should be greatly smaller than the relative dimension of the data domain here. And here is a simple compression example that we can take a look at. So in this case, our input data is a smooth vector field. And we show the blockwise PCA method and the clustered PCA method over here. And how these methods work is that blockwise PCA takes the input domain, it splits it into fixed size blocks, and then it computes a PCA basis for each block. And these PCA bases are independent, and that's why you see the cluster discontinuities between these spatial clusters. On the other hand, you have clustered PCA, which doesn't use any spatial domain blocks. It simply operates on the data vectors themselves. It clusterizes the data vectors into coherent clusters using a distance to subspace measure or metric. And then it computes a basis for each cluster. And what you see here is that it adapts slightly better to the data since it didn't assume any sort of spatial cluster shape. However, since the clusters are independent, you can see these cluster discontinuity artifacts between the clusters. And this is what we refer to as the cluster discontinuity problem. And the main issue here is that in both of these methods, the clusters are independent. So the reconstruction model, it tries to obtain this image, but it's unable to do so because the clusters are not cooperating or communicating with each other. And this cluster discontinuity problem is not unique to the linear dimensionality reduction methods. In fact, it turns out that this is kind of a fundamental issue in a wide range of related methods. And we discuss all the related methods in more detail in the EGSR 2021 paper. So you can find more details there. But the key idea that was inspired by all this related work in this area is that what we want to do is to incorporate this interpolation and smoothness condition to the model right from the first principles. Let's go over how we do that. So the starting point is the same as before. So we have some set of data vectors that live in this high dimensional space, and we seek a simple linear combination approximation to this target data. This is where things get interesting. What we do right now is that we assume that the target function is a piecewise smooth function over some low dimensional domain like R2 or R3. And then we take this basis decomposition and write the coefficients and the basis vectors as a function of the target domain. Okay. So the next step is to take our reconstruction formula over here and write the moving coefficients and the moving basis vectors using a kernel expansion for each. And if we choose to use linear hat kernels, this is the image that you would kind of get. So you have a few hat kernels for the basis vectors that have a large spatial support. And then here you can see a lot more coefficient kernels that have a smaller spatial support. The key thing here is that the basis kernels overlap, and this is the property that allows them to share information during the reconstruction. And the same thing for the coefficients, they overlap with their neighbors. The other key thing to note here is that there's a lot of coefficients that fall under the support of this basis kernel right over here. And this is the key property so we can obtain compression, because we only need to store the coefficients for a smaller set of kernel basis functions that are high dimensional, and then we can store a lot of low dimensional coefficients. So all in all, what we get here is that the moving basis decomposition is defined by these two sets or sequences of kernels. So we have the kernels for the coefficients, we have the kernels for the basis vectors, and we have their corresponding coefficients. And you can see how the kernels and the coefficients come into play in these kernel expansions over here. And then this is kind of like an illustration what the ending approximations might look like. Okay, to make things a little bit more concrete, let's take a look at a really simple example where our spatial domain now is just the interval from 0 to 1. And if we use maybe the simplest possible kernels you can think of, just hat kernels in this interval, they are positioned at 0 and 1 respectively. And in this case, for simplicity's sake, we use the same kernels for the basis vectors as well. And in this case, we can explicitly write out what's the moving basis decomposition. And the sequences for the kernels are shown here. It's just the x and 1 minus x for both the coefficients and the basis vectors. And then we have the coefficient tensors for both of them. And if we take our reconstruction formula and write out it using these basis kernels and coefficient kernels, this is what we get. And you can see that using these simple linear hat kernels, we end up with a quadratic model. And you can kind of see that this moving basis decomposition model is more expressive than a simple linear basis decomposition using linear basis kernel functions. So in some sense, you can think of this as a generalization of linear basis decomposition models. Okay, now that we know what a moving basis decomposition is, the next question is, how do we obtain one? And how do we compute the moving basis decomposition? So given a fixed target function and some fixed kernel functions, what we want to do is minimize the reconstruction error over the spatial domain. And in general, this is more involved compared to other models where the clusters are fully independent, since now we have interactions between the clusters. And what we are minimizing here is the pointwise reconstruction error, and this integral is over the spatial domain, right? And the error is measured as the square norm of the difference between the target and the approximation. Now, even though this is a global optimization problem, it has a really sparse biconvex structure. And that helps when we are solving the problem numerically. And the sparsity, it comes from the fact that the basis kernels and the coefficient kernels, if they have compact support, they only overlap with a few neighbors instead of all other possible kernels over the space. And that's what introduces the sparsity. And that's a key property when you're picking the kernels. To solve this optimization problem, we use a quasi-Newton solver with diagonal Hessian approximation. And it turns out that the gradients and diagonal Hessian elements have simple forms. And you can either solve those analytically, or in our case, numerically with Monte Carlo integration. And you can find the details of the solver in the EGSR paper, but the key point here is that this solver scales reliably for very large problems. For example, our production scenes have routinely over 100 million unknown parameters, and it usually only takes a few minutes to solve this MPD problem. That is, the problems obtaining the coefficients for both the basis functions and the basis coefficients. Okay, so at this point, we are ready to revisit the cluster discontinuity problem we saw before, so we can appreciate the value of this moving basis decomposition model. And again, here you can see the reference vector field, as well as the clustered PCA and blockwise PCA approximations that have these blockwise or cluster boundary artifacts over here and over here. And this is the moving basis decomposition solution, and it's virtually the same as the reference one. Now, interestingly, we can cut the number of the clusters in half, and you can see the result in blockwise PCA as well as clustered PCA. In contrast, moving basis decomposition, it remains essentially the same, so it reproduces the reference very closely. And moreover, if we look at the relative MSE numbers, we see that in addition to being visually close to the target function, it converges in terms of the relative MSE. It has the lowest relative MSE amongst the comparison methods here. Now, this is another toy example where the input data is an RGB image, and the output is compressed using really large 64 by 64 pixel blocks and 2 basis vectors for each block. So the 64 by 64 block is roughly the size of this square over here. The point of this comparison between the blockwise PCA and moving basis decomposition is to show that these hard blockwise cluster boundary artifacts, they are very visible in this case when we use large clusters and a low number of basis vectors. However, if you compare that to MBD, you see that this hard cluster boundary has now turned into this smooth gradual ramp that's visually not as visible or striking. The main application of moving basis decomposition is compression of precomputed lighting data. And in this case, the lighting data input is a light transport volume where the light transport data consists of direct light transport matrix and the indirect light transport matrix. And these matrices or operators are stacked into a single really high dimensional vector. So in this case, if we stack the direct and indirect light transport matrices, where the indirect light transport is per color channel into a single vector, we obtain this 324 dimensional vector. And now the output of the algorithm is an MBD basis and coefficients, and we compare MBD against blockwise PCA, windowed PCA, and clustered PCA. And one thing to note about these comparisons is that clustered PCA has to use more memory with the same number of basis vectors since it needs to store the cluster index. Whereas blockwise PCA and moving basis decomposition, the cluster indices are implicit because they are encoded by the spatial clusters in case of blockwise PCA or the spatial kernel functions in terms of moving basis decomposition. So this is the first test that shows the direct light transport results. And so there's a couple of things to note. If you look at the overall error using 4 basis vectors, we see that the MBD has the lowest absolute error over the image space. And if we look at these zoomed in regions, we see that the comparison methods, they all suffer from these cluster discontinuity artifacts. While if you look at the moving basis decomposition results, you see that the cluster artifacts are now gone. And what we have is something that is visually and numerically really close to the reference solution. Now, using the same light transport matrices, we can look at the indirect component of the lighting. And this is the reference lighting environment where the direct lighting is shining at an angle. And again, we see that the moving basis decomposition results in the lowest absolute error over the image plane. And if we look at the relative MSE as the number of basis vectors changes, we see that the MBD competes very well with the clustered PCA, even though clustered PCA, remember, is using more memory since it needs to store the cluster index. And finally, we can take a look at the close-ups here, and you can see that the moving basis decomposition, again, doesn't suffer from the cluster discontinuity artifacts, and it's visually and numerically close to the ground truth solution. And here is an interesting example where we changed the support size of the kernels or the support size of the clusters in terms of block PCA and windowed block PCA. So 9 by 9 by 9 here means that the clusters are small or we have a large number of basis vectors or basis kernels. If we increase the basis kernel support or at the same time decrease the number of clusters, what we see here with the comparison methods is that the cluster artifacts are becoming more and more visible. And you can see this visually, you can see this in the false color image, and you can also see this in the relative MSE numbers over here. So it's very clear. On the other hand, what's interesting here is that the MBD is it's most robust to these kinds of changes. So yes, you see that it degrades in the error a little bit. However, visually, these images are very similar. So the key point here is that even when you change the spatial support size of the clusters, the image or the end result is robust against these changes. Whereas with the comparison methods, the artifacts quickly pop out and start to dominate the image. And finally, we revisit the real-world example from Black Ops Cold War, where the source data was 1.5 gigabytes. Now, this is rendered using the moving basis decomposition reconstruction done per pixel every frame. And we are using roughly 1 byte per voxel, where
where our input data was 48 bytes per voxel. So the compression ratio in this case is roughly 40.1. The key point here is 1 byte per voxel for RGB linear SH irradiance. So that's fully directional RGB irradiance data with 1 byte per voxel. The most interesting bit, I think, of this application is that the basis kernels here, they're actually in 2D. So if you recall, in the beginning of the talk, I talked about how we use this warped irradiance volume. Now, we simply use the 2D planar projection of this warped irradiance volume to define the spatial domain of our basis kernels. So they are just two-dimensional functions, which cuts down the memory usage even more. Now, since we do want to have reconstruction everywhere in the space, the coefficient kernels, they are just 3D hat functions, and they correspond to the texel resampling functions for the 3D volumetric texture. So this kind of demonstrates the power and flexibility of the moving basis decomposition framework, where you can mix and match the sizes and shapes and types of kernels. And the solver framework is kind of, if you write it in the right way, you don't need to change the solver while doing these changes. And that way you can have adaptive basis functions if you would like to have so, or different basis functions with different dimensionality as well. And then this is the final example I wanted to show. So this is from Warzone map, and this is one of the nighttime maps. And what you see here is actually using the moving basis decomposition to reconstruct the lighting. So in this case, we can actually see that in a nighttime map, there's a lot of direct light sources, and these are actually encoded in the irradiance volume as we have. So you can kind of appreciate the resolution of the irradiance volume that's encoded with the moving basis decomposition. And the fact that you can have like a lot of point like direct light sources baked in. So Vista views like this, you can actually ship these with 60 frames per second, since you don't have to use runtime dynamic lights to represent all these small light sources in the distance. And yeah, and this is just another result of the same idea. Okay, so I kind of wanted to summarize what we talked about here today. So we started with how we represent and sample irradiance. And I think the key idea there that if we take this probabilistic point of view, we end up minimizing the reconstruction error over the expected view position. And this kind of lets you sidestep the issue that you can't solve the fundamental light leaking problem with volumetric representations. But if you take this a priori distribution of view positions into account, you can greatly minimize the resulting light leaking artifacts that happen after that. The next thing we touched upon was how we use this reproducing kernel Hilbert space approach to solve for constrained SH projections. And by introducing these color space constraints in addition to non-negativity constraints, or instead of non-negativity constraints, we saw that this framework where you can solve the constraints in this spatial domain representation can be really useful and kind of powerful to encode several different convex constraints. And it's simple to implement. So I would encourage you to experiment with these ideas too. And finally, we presented the moving basis decomposition, which is kind of like a generalization of existing linear basis decomposition models. And it gives you efficient and seamless compression for high dimensional data. Now, the key point here is that we take interpolation and the moving basis vectors into this model into account from first principles. And then we solve the optimization problem, whereas a lot of previous methods, they do the dimensional reduction, and then as an after step, they try to fix these artifacts that happen due to the properties of the dimensional reduction. And one property is that if the clusters of your dimensional reduction method are independent, then the clusters can't cooperate when you're doing the reconstruction, and then it's likely that you will have some sort of cluster boundary or cluster discontinuity issues. And if you're interested more in this thing, I would encourage you to see the EGSR talk and the EGSR paper for more details. I include it in the references at the end of these slides. Thank you for your attention, and thanks, Natasha, for organizing the course this year. And We are hiring, so if you're interested in discussing more about these topics, please go and see careers at activisionpsarc.com. Thank you.
To wrap up for the day, I wanted to thank, first of all of you for listening to the talks. We appreciate your attention. And I also wanted to thank all of the speakers and contributors who worked so hard on preparing outstanding talks that you just saw. Tomorrow, we'll resume the course with a part 2 talks. We'll begin the day with Jasmine Patry from Sucker Punch Production, who will share how they brought the Ghost of Tsushima production alive, using new approaches for performing diffuse and specular indirect lighting, atmospheric lighting, and rendering techniques for haze, clouds, and particles with multiple scattering, and more. Next, Daniel Wright from Epic Games will break down the set of techniques behind the real-time global illumination approach of Lumen, centering on the fast final gather method combined with ray tracing that's targeted at the latest generations of consoles and PCs. Lastly, Henrik Halen and Kyle Hayward from Electronic Arts will present a deep dive into a different approach for real-time GI using circles, and how they've extended the approach to compute scalable, stable global illumination for dynamic geometry, skinned characters, and transparency in real time. We'd love to hear what you thought. Please share your impressions using the RTR Advances hashtag on social media. The slides for the talks will be posted by the end of the week on the Advances website. The videos will find their way to a new YouTube channel for Advances in real-time rendering. Please also take a few minutes to fill out the evaluation forms from SIGGRAPH for the course. In just a few minutes, your thoughts really can help shape the course for the future, and to help SIGGRAPH hear the value it may provide for you, and help shape the conference itself. We really appreciate learning what you thought worked and what could be better next year. What topics do you want to see in the future Advances? Thank you. I wanted to extend my deepest gratitude to a number of people who helped bring this course from its inception to completion. Paul Jeremias, Leona Caffey, Chris Redman, and Carlos Gonzalez Ochoa from 2021 SIGGRAPH Organizing Committee, Eric Haynes and Thomas Akinin-Muller for hosting the Advances site for almost 2 decades, Sebastien Lagarde and Peter Pike Sloan for helping shape the course and provide invaluable feedback, and Unity's AV team for helping prepare the content in the video form for the virtual event, Ali Brumer, David Boisvert, Leo Parent, Julian Carvajal, Len Zelinsky, Leif Thompson, Heather Glendeling, and many, many thanks. Next, we'll have a live Q&A with all the speakers. There you can ask your question to a specific speaker or pose the question to all the speakers in the panel.